I would, I would say now more or less complete, but still we have to go long way, because many of the things where there is like qualitatively much better, but we can do much better quantitatively, and that's where the Aditya-L1 comes. When we are seeing any surface, any solar atmosphere, we know we need to get this observational data and everything, because we are not directly seeing the inside. So by doing model, if we can match the observational thing, then only we can see these the models are perfect. So this is kind of idea from here. So now if I go to the next slide, not going slide. Yes. So how do we come to know this structure? So we'll go step by step. So here I'm showing you the photosphere, the visible surface. So probably all of you know, since you are interested in solar physics, so you probably have seen this. So these are sunspot, faculae, many things. And if you zoom out, then you will see these are sunspot structure, granulation, intergranulation, everything. But when we see from the telescope, we only can see this part, right? So now all the surface features, they are happening. That is actually happening because sun is doing a lot of physical procedure inside the sun. And that is actually coming. So in the daily to daily example, you can take boiling, how do I say, boiling milk. You'll see that how it evolves and everything. So it is not the same picture, but qualitatively you can analyze that everything happening which is inside, that is you're seeing at the outside. So that's why we need to develop theoretical model. So again, that comes with your daily understanding of the energy conservation, momentum conservation. Again, you have to go back to Newton's law, that how the momentum conservation, this mass conservation, everything is comes into picture, and how we are going to apply it there. So this is kind of, then we can model develop this theoretical model, and then we have heliosismology. So any of you has idea how we come to know that inside our Earth, what are the things, what are the we have core, we have crust, everything. How do we come to know about all the seismology, right? In the similar way, we can do the seismology in the sun. But since it is, as you can already presume, that it must be much difficult, that's why it has not come from last 100 years. It started, the first idea came around 1960s, but after that, from 1990s, it came like very nicely. So now I'll show you one of that how much we have come from 60s to this 2023. So this is, I'm showing a visible spectra for the sun from Kitt Peak Observatory, and it is from 1968. And this resolution is like 5 angstrom. So nowadays the resolution was 0.05 angstrom. So you have like huge amount of data. But just imagine in 62, when we are seeing the sun, we are seeing this visible spectra, and within 5 angstrom, we have so many lines. So this gives us the idea that what are the chemical composition, or what are the composition the sun has. So here I'm showing you like few examples to give you idea that in 60s we had this much good. So now if you see, we have tremendous amount of data to understand what are the things happening on the atmosphere. So using this spectroscopy data, actually we can understand what are the composition of the sun. So whether it is hydrogen, helium. So these are the main thing, but they have more material. And if you any of you has done like the basics of astrophysics, then you know that apart from hydrogen, helium, whatever things we have, we term them as metal. So X, Y is like hydrogen, helium, then all other things, because they are like very small percentage. For the sun, hydrogen is mostly 75, and helium is around 20, and other things are all other things. So now what I'm thinking, that now I have this data, I have all this observational stuff. So I want to do theoretical modeling. So now I have pen and paper, I have some physics understanding. I sit down and I take the sun spherical structure. So what I will do? First thing I will do, I will see that all the physical laws, I will start doing it. So whether the mass conservation is happening. Suppose you are seeing the flow, when you are seeing the sun, energy is also coming from the sun. So whether energy conservation follows. So if there is energy coming from the sun, there should be some energy generation. Otherwise, suppose you're like, suppose you have a heater, suppose in this heating, and you're heating some source, and you switch off your heater, so it will go away, right? It's just radiate away and it cool down. So you have to do with the energy conservation too. So there must be something which is generating energy, so the sun is brightening all over. Like it's 4.6 giga-year old and still brightening. So we have to do this one. And also remember, the star and sun, everybody is like all equilibrium, like mechanical equilibrium. So they are not collapsing. So this equilibrium also you have to take care of it. So as a physicist, you always want to go with the physical laws. Then if you take these three, then you can derive and you can understand how these things are going. But problem is, you know all the methodology and everything, but you cannot handle the parameters. Suppose for developing these things, suppose you want to do how the density. So if it is only consists of proton, you just take the proton and you see the total density, you can get the number density of proton. But things is not this straightforward. So you have the proton, nucleus, everything. So then physics is known, but it's very, very complicated to work out. And then there comes the supercomputer nowadays. So you have to solve all the equation in like explicit form with the time, with space, how things are varying. So this is the idea. And when we develop this theoretical model, actually after developing theoretical model, you are doing, suppose for the present sun, you are seeing the sun as it is in 2023, you developed a model, you see how these things are happening. The sun is evolving. So with the time also you have to develop a model. So when you're developing the time evolution, so there is a star, the stars are also born and goes like the main sequence, then red supergiant. So whether that scenario also following your theoretical model, whether they are also takes care of that. So that also you need to verify. So three things take away from this slide. You need to see for the system what kind of observational detail you have. These are your verification. And then your physical laws and whether this physics is valid there. And the third point is the evolution with the time also, whether it is changing. So this theoretical model which I build, I'll take through you. I'll go through this. We find that actually matches the stellar evolution too. Any question? So feel free to ask me question because this is supposed to be very interactive. So if you have any issues to understand that, so I'm taking you from very fundamental. Suppose I'm there and I want to study stand. What I will do in this way. If you have any question, you can ask me. Yes. Then I'll stop. I'll ask question and I'll give you 5 minutes to derive it. So then if you go the equation. So now I'm coming to the equation. So that's why I made some notes because I have to go through this little bit of physics. So here you see, this is the first equation. So suppose you want to see the sun, and the sun is the plasma, gas or plasma, right? So if you want to see how the inside and everything is changing, what you want to study? How the pressure is varying, how density is varying, the thermodynamic quantities. Because if you have the density, you know that how much density spread over region, you can get the mass. So our main idea is to get the density, pressure, and from mass you can get the density and energy. And if you get energy, suppose you have I give you a box, and inside many of the particles are moving and randomly going. So if it is achieve the thermodynamic equilibrium, the energy is 3/2 nkPt. So whether that can be used. So if you know the energy, then you can actually calculate. So now if I ask you the first thing, you see this is the first thing is the pressure equation, right? What does that mean? So I give you a sun, and the sun is like gravitationally self-gravitational body. So it is contracting again and again. So if there is no support from inside, the sun is like different layer, it will collapse, right? So that is called the free fall time. So if sun doesn't have any pressure to balance it, you see within half an hour sun will collapse. But is it collapsing? No. So we have something to support it. So this pressure gradient actually supporting your the self-gravity thing. So how you will derive it? So as a physicist, so what we do, you can start deriving if you want. So what you can do if you have a star and take a small mass element of Bm. So I can, that's what I derive here. So I can ask you to do this. Then you can understand how sun is actually in equilibrium. So suppose that you take this small mass element, its mass is dm, and area is a, and this is dr, like the width. So this is in the convection zone anywhere. So your dm should be like, if you know the rho and r, so that will be a dr, right? So this is your a. Now I assume the pressure in this layer is p, and there is p plus dp because it's a small dr. So you have to calculate how much the gravity. So in principle, this mass element can be equilibrium only if the gravitational force and the pressure force are equal, right? So in principle, you can write FGR that equal to AdP. So that is your net force because the pressure variance is dP and A. So you can suppose I give you one example. I'm standing there. How much pressure you're putting on this thing? How can you calculate? Force. So how much force I'm giving there? My weight and it's into G, and that by how much area I am taking. So in the same way, so you have area A, so you have the pressure dP variation, so you have net force AdP. So now you write how the gravity looks like. So the gravity is like minus G. That's why I say M in radius R, because I'm taking the solar interior. So at radius R, how is the mass? You write MR, and then your small mass element. That by R square, that will be AdP, right? So now you replace this dm by this. So then you'll see that this equation is coming. And dm is a small element, which is like, of course, with a if you write this A as the 4 pi R square dr rho r, that is you giving a dr. So that is very simple equation to derive, and it gives so much fundamental understanding of the sun, that how it is just not collapsing the pressure. And now I give you another question. How you are going to measure the pressure inside the sun? Have you thought about it? So suppose you're doing a lot of atmosphere and everything, but how do you know the pressure and temperature? So these are the equation which will give you. So I'll come into this, but this is the pressure equation. And then if I go to the next part, this is your energy conservation. Now remember, as I was saying, this L is the luminosity. So if you see the sun, in each second, sun is losing 3.8 into 10 to the 33 hour per second. That is the luminosity of the sun. So this much energy sun is losing. So if you take the radial variation of this luminosity, it must be equal to this epsilon. This is the energy generation rate per unit mass. So you are multiplying with the mass. So you are getting the total energy generated in the core. So that gives you the energy conservation. And now here I wrote the how this luminosity looks like. So this is 4 pi R square. Now remember, you have the radiation, which is coming with the radiation transfer and the convective transfer. Both of them are included. Because remember in the first slide, I said there is convection and the radiation. So that's why two parts you need to take care of it. So now you can, I will come that how we know that actually it is radiating and the convection, both of them, how we get the convection zone width and everything. But this is kind of idea of the energy conservation. Now I'm telling you this is the nuclear energy generation which is happening. That is, how many of you from master student? So you have all of them. Oh, perfect. Then you all know about the nuclear physics and the PP reaction, CO reaction. And you know that when this reaction happens, they produce the mass, rest mass energy getting transferred into the energy. Einstein in the GR or whatever. You guys did it. So I'm not going through detail. But I impose one question there. So why the sun is suitable for nuclear PP reaction? So I am telling you it is happening. So why? And then how do you know that it's indeed happening? So think about it, like why, how do you get it? And I drink water meanwhile. Any answer? But what are the conditions needed to do that? Exactly. So the first equation which I was telling, you have to actually get the temperature. Then you'll see that the stellar structure equation actually giving the temperature to hold it. And another thing I want to mention, when like sun is collapsing, like due to gravitation, and pressure is balancing. So with the time, you know that it evolved and it may synchronize. So this gravitational contraction also can give energy. So you can say that that contraction energy can also power the sun. Because a small element, if you're taking from the infinity and bringing against this gravitational potential, it will do work done. So this work done can give the energy. So we can derive that too from the pressure equation. So then we see, like I'm giving you an answer. So if you do from this gravitational energy contraction, then you will see that energy will not be able to sustain the sun more than 10 to the 7, like 10 to the 6, 10 to the 7 years. So that's why, and if you calculate the temperature, you'll see 10⁶ or 10⁶ in the central temperature. That is much more suitable for the nuclear reaction. And also, if you see the nuclear reaction from the resistance energy, how much energy it is producing, and if you do the time scale, it can survive the sun more than 10⁻10, so more than gigayear at the present age of the sun, and it can still fuel the sun. So this is kind of indirect evidences. So that is kind of, how can I say, circumstantial evidence. So you are studying from theoretical model and everything, and you are getting it. But to get the direct, we have to go for the high energy physics, and we have to probe them. And how we probe? We probe by the neutrino, because PP reaction and everything, they are creating the neutrino and everything. And remember, all of the equation I showed, I assume the particle are the non-relativistic particle. So if you go for the de Broglie wavelength, so the electron or proton, the de Broglie wavelength is much smaller than the distance between these two particles. That is one kind of assumption. But if you do correct for them, still it will valid for this scenario, because this energy is not that high that the general relativistic or things will be too much important. Okay, so then, so I will ask you to do something so that you can get idea, because it's supposed to be interactive. So you know that I gave you this equation. So you take this equation, and if you want to get the gravitational self energy, so you multiply both sides by 4 pi r cube dr. Do it, everyone. Then you will see that how the mean pressure is related with the gravitational energy. So I can, I'm just erasing this. So this is to take you towards the standard solar model. So what we're saying this, so using this all the structure equation, actually we can make a standard model where you can get all the pressure, density, temperature, how it is varying inside the sun. So you will get some idea now. If you multiply this 4 pi r cube r dr and integrate from to 0 from center to the surface, integrate it. So I write the answer. So you know so you are now doing 0 to r. So r is the radius of the sun. So I can put this. So I'm multiplying dr with my dp dr, that equal to minus g . So this is, if I remove this, you see this is now giving you the gravitational energy, right? So that will be your E gr. Of course, if you integrate, and remember, this integration is not that straightforward because your rho is dependent on the r and everything. So only you can calculate it as if like you did in your 10+2 or undergrad. If you take rho equal to constant, then that comes 3/5 gm by r. Remember? So that counts. So now this integration, if you do, you'll see this will come. Final answer I'm writing. This will come as 3. Oh, I just do the main thing. So 3. So integration by parts. So d of whole thing. So you'll find so this will come. So this is your volume average mean density. So if I write it, that will come as like 3p. So I can divide it by v to get the mean average over the solar radius. So that will give 3v, and that will be EGR. So this is called the virial theorem. So how from the self gravity you can get the mean pressure? That will be minus EGR 1/3 by v. So volume of the sun, you know, gravitational potential, gravitational energy you can calculate if you put rho equal to constant, just for simplicity. But if you want to do like exact calculation, you have to do in computation. So if you take the rho equal to constant, then this can be easily calculated. Now remember, this is the mean pressure. So if I assume the equation of state and inside, that is like the ideal gas. So PV equal to 3/2 NKT, you can get temperature from it. So this is very important one. So pressure, temperature, everything you can get. So now, so suppose you are taking this. Is there a question? Yeah. Oh, so this is this is the mathematical brilliance. So if you want to get the energy, the gravitational energy, then we are doing for simplicity. Surface of this into dr, the surface, suppose small element you want to bring. So but you see there is a force r square, so that's why. But you can assume that against the force you're bringing a small element dm, that you can assume. So now if you assume this nkt, so from there you can get the temperature, and even if you replace your thermal energy is like 3/2 nkt, right? So now you can replace thermal energy, you can relate pressure with the thermal energy, so you can get the thermal energy from here too. So now you can say how much thermal energy actually sun is creating, so from this calculation. So I can just, this board is so small, I just I'm erasing this, so you calculate it, right? So now if you see this one, so I just write the final answer, that is better. So the thermal time scale, that equal to your E thermal divided by L sun. So this is the radiating away and this is the energy. And that will give you 1.6 into 10⁻⁷ years. And if you calculate the temperature from here, the temperature is also coming as 4 into 10⁶. So this is actually good for nuclear reaction to go on. It's fine. Yes. So this is kind of, from your undergrad physics or from the fundamental momentum conservation, everything you can actually derive. So that's why we are saying that thermal energy due to gravitational contraction will not be enough to hold the sun against its collapse, and we need nuclear reaction. So now come to the energy transport. So this is again very simple. So I think you can relate it. So suppose the energy, now I know that the nuclear reaction is happening, and with the energy generation is epsilon, and epsilon is coming from the pp reaction. Now once this energy coming, then how the energy is getting out? So you need to do the radiation transfer. So here you see, suppose a photon is going for a direction with a length dx, and the target atoms are this, and it has density n. So how much interaction it will go through? In sigma dx, sigma is the scattering cross section by all these target atoms. So when photon is going, if you take a projection, it will come across the scattering cross section, and it will scatter with this. So this is your number of interaction. Now, mean free path concept, I think all of you know that the distance where the photon will go without being scattered. And now you put like the distance dx equal to 1, it's not scattering. The mean free path becomes 1 by n sigma. So that is the concept from here. So the photon cannot travel without getting scattered is only this mean free path. So I'll calculate, you see here I have calculated the mean free path. So now here also I summed over, because when I'm telling the number density, maybe one species, hydrogen might be there, and the number density of this is hydrogen. But in general, it has hydrogen, helium, and everything. So you have to sum over this number density. And then for each species, there will be sigma. So that's why this term comes. So that is the density, mean density constitutes of all of them. And this is the opacity, which you can calculate for the all material. If the sun is only hydrogen, not other thing, that will be very straightforward. Hydrogen property and everything. But that's why when you do the realistic radiation transfer, so you have to take care of that. And for the sun, so now you know that this is n. So I am assuming this now, the simplicity. So now I'm assuming this is full of hydrogen, and if they only 1 electron per atom, then you can calculate this how the n, sigma, and everything looks like. You see, it's at 2 centimeters. So it cannot go more than 2 centimeters. But we have the sun and everything. So if you calculate everywhere, we see the solar photon can travel only 1 millimeter. So it's like the more realistic calculation if you do all of them. So that's what I was saying. The photon cannot travel inside the sun without getting scattered to a new direction within 1 millimeter. So this is like the random walk problem. A drunkard is going and he is going this way and that way. At the end of the day, how much he crosses? It depends how much steps he is taking. It's not the straightforward steps, like going there, again bumping his head with one of the lamppost, again going. So you have to calculate the mean free path. But here, the direction is very random. You cannot do a vector sum. So if you do, this is the scattered, so you cannot do a vector sum because it is at the end of the day, it goes 0. So you have to do the mean, the square of it. So in square of it, you see all the cross products, all the dot products with the other direction goes 0 because as a whole you're considering. And this D become the all of them NL square. Now you remember, you know L. And D, now depending on the how many number of steps photon is taking and how much mean free path, you can calculate the distance, how much photon can travel. So from there, actually, we can calculate the how much distance photon is covering via radiation without getting the convection. And now I give you this question. Can you estimate how much time a photon will take to emerge from the sun? This very popular problem when we were in masters we did. And here also you can do. So how you will approach to this? That will give you time and how many steps it is taking, how you calculate. So you have distance, solar radius, and your mean free path is L. So number n is like radius by n. You know the number of steps. And photon is moving in the velocity of c. So what is the time scale, you know? So then you can calculate how much time it takes. Is it okay? Or I repeat, it's fine. So then if you calculate, so then I calculated, you see it takes 52,000 years. So what does that physically mean? So if nuclear reaction stops today, for 50 years, you won't understand anything because the last photon which is just emerged from the nuclear reaction is still traveling, it is scattering and everything. So this is the radiation process. The photon takes this much energy to go through that. Yes. This one. Oh. Oh yeah. So that's what you know that here. So here I calculated 2 centimeter, assuming it's the mean density, all the mean. But when you're taking the hydrogen, helium, and everything, that density increases. So that's why the opacity. Oh, we put this in the opacity calculation. We put like hydrogen, helium, all the components. Then we get the opacity from the helioseismology and other. Then we put it. But for your like simple understanding, this is the way we do. Then so this is like takes 52 years. So that is very interesting that photon takes that much time. So now can you calculate how this energy conservation thing? So now you have this idea and this background how photon goes. So suppose you have 2 layers, which is close to the center, it is the more energy, is the energy density, which is going a little bit after is the energy U. So energy is flowing through this LR. So then here I define what is LR per unit time. Your U is the energy density and delta U is the excess energy density. So now you know that this is the energy and this is it takes time to cover this delta distance. So you can get the total energy, how it is crossing. So then you get this equation. So this is the energy conservation. Now here we did another trick, which is may not be true inside the sun. So we assume that inside everything, sun and everything is under thermodynamic equilibrium and it is a black body radiation. But it is not true in all states. So then if it is under black body radiation, then you know how much energy is coming from the sun, you can estimate using Stevens-Boltzmann law. Is it? So then you know that sigma T to the power 4. So if you know the temperature, so we replace this, then you get the temperature equation. So this is your temperature. Now, how many things you get? You get the pressure, you get mass, you get temperature. So you're almost ready to go to build your standard solar model. But remember here another thing, all of the quantity, they are not independent of each other. So if you only solve temperature, it is directly related to the pressure. So that's why they're all coupled equation. So to solve the solar structure or interior, you can never solve only one equation. So that is these 3 set of equations, they are called stellar structure equation, or for the solar case, we tell them solar structure equation. And from 60s, people are solving them to get how they look like, radiation beyond convection zone and everything. Then there is another thing comes, the convection. So this is the criteria I write. So convection, I do not want to go to derive it. It's just like some blob when the radiation energy is coming, then the blob is getting some energy, and that just imagine the water heating problem, but it is much complicated. That is the thing. So water heating problem, the heat is getting some tiny blob is getting like displaced because of the buoyancy going up and again going down. So this is the efficient energy. So Schwarzschild derived this condition that in which temperature gradient that actually will be fulfilled. So this is called the convection onset. So, and you see, it depends on the pressure and even each layer of temperature. This T and P are function of R actually. They're not constant. So, and the DTDR, whenever they will be more than this, the convection will start playing. And here I wrote few of the things. So how do you understand where the convection is starting? Actually, we can get estimate of this radial gradient. So when the radiation energy is going, so there is a mixing. So opacity, if you go like up and up, the opacity also changing. So if opacity changes, the radial gradient also changes. And by measuring this gradient, actually you can say where the convection is happening and where the radiation is happening. But provided here we are all saying theoretical. I will show that heliosismology actually finds it. So that is the beauty of physics, right? You are developing a theory and everything, and then you do not know whether this is valid. And some maybe after 30, 40 years, when we have this observational detection, you go and see that, oh, our fundamental understanding was so correct. So that happened. So this theory came 60s, maybe Schwarzschild, I do not remember, around 50s. But now with the heliosismology started 90s. So in the 2000, we actually got that, oh, whatever they predicted, everything is correct. But remember, there is no biasness either, because people are like very clever to probe them. And heliosismology is like the pulse. I will come to this pulsation there, and you need very accurate measurement to do that. So this is, and another important part is when convection sets in. So that it you will do one experiment, you can understand. Suppose you are doing this heating, you put like little bit of black ink or everything. You see everything will mix together. So convection always mix them. So create a homogeneous system. And also lecture 2, I will tell you that this is so much important for the magnetic field generation. Because if you see the solar atmosphere, everything is magnetic. So there are like famous scientists, they say if the sun doesn't have magnetic field, we won't even study them. So that's why in the convection is like very important to understand how things are happening for the solar dynamo. And remember all of these things, I have never considered any magnetic field, any rotation. These are like simple structure equation to understand overall density, pressure, and this variation. This is just to probe the interior of the sun. Oh yeah. So we are assuming this is the convection. This is like a full of the equation of state and everything, and we are assuming this has a gamma. So this is like the adiabatic indexes. So when the convection happen from one to other, we assume in this part there is no exchange of heating. So that's why it's the adiabatic condition. And this is the polytropic index, gamma, Cp by Cv, and this is your Tp. So whenever this radiation goes in, this process can be possible. But if DTTR is less than this, then this blob will never go out. So this is for the buoyancy to set thing. So very fast, exactly. And that is actually true. That's why you have to, when you will do like convection simulation, actually you'll see sometime it doesn't valid. So we say super adiabatic, sub adiabatic. So this kind of thing also you have to take correction of it. But in general, for the interior to set scene, you can say that this is true. That is from here. From the opacity and everything, we can only calculate the DTR from theoretical. The pressure we can calculate, temperature we calculate. Then we see how this radiation DTDR and everything varies, the gradient. No, we have the 3 structure equation. You solve them by giving some initial composition, and you see whether outcome is coming. Like the photosphere, you see everything, and where you calculating, you see that temperature is it has a radial gradient. So then you can calculate the gradient. Suppose you get temperature, pressure as a function of R, you can do the DTDR, DPDR, and you see in which condition these conditions are followed. And then you see that after certain region, this DTTR actually changes from radiation to convection. And that is again, as I said, this theoretical estimate. So then heliosismology comes in and actually probe that is correct. So that I will give you a comparison that how the theoretical model and the observation comes in. Any more questions? Okay, so I go to the next slide to a standard solar model. So now you know that all of this equation and everything, now you are ready to jump into the standard solar model. So now you can compute them. So here you see, with this structure equation supplement, so now you need to put the auxiliary input physics, like what you are getting from the observation. Suppose the surface composition, how much hydrogen, helium, everything. You can put it. Then you can calculate. Another thing, as I said, outcome of the results should satisfy the observational constraint. Like suppose your structure model give a radius of like 10 times sun, then we won't believe it. And the luminosity, if it is not giving 3.83, which we can see, luminosity is the correct version of the observation, because that we do not do anything, because you can see it from the earth. You can calculate, so that should be valid. And this chemical abundance is what I'm saying that we get from the observation. So these things from your model should be valid. Spherically symmetric may not be true, but it is true for the sun. Its oblateness is not that much. These things, when you come into the picture, you'll see that some of the results might get changed, because magnetic field is a beast in the solar interior, because it does everything. So that I will come step by step. Mass loss and the tidal forces. What do I mean by that? You know, the sun has the solar wind, it's going off and off. So with the time, it's losing mass. So am I correcting it for the model? We are not. For this, not. Tidal forces. If you see any planetary system and other thing, now in the exoplanet area, you see many of the hot Jupiter which have been discovered, they're tidally locked. And they are actually giving perturbation to the host star. And this is some of the reason why host stars are like just getting deviated from their spherical structure to other things. But this tidal force we have not considered. But these are ongoing research. Like suppose you guys are interested to modify or something, you are welcome to do so. Like you just go do some calculation, and you see that at the end of the day you cannot solve it on pen and paper. Then you do coding, you computationally solve them. Then you can understand that these things also indeed play a role. For the sun, probably not, because our planets are far away. But if you see other sun-like star, is that a very big hot Jupiter is like orbiting, you see it does affect that. So these things are like our assumptions. So now we made this. Now let's see what are the results is coming. So here I show you the result. This paper is from, or did I put 1999? But now standard solar model has increased a little bit. I just wanted to give you that the very old papers, because how people have, without having this much instrumentation, without having this much observation, how did they formulate it? So you know, just imagine the Aristotle time. How do they measure the sun or distance in that way? So they are like, they develop this, all of this kind of thing. So then if you see, this is the temperature profile. You see at the center, it's the 10⁻⁷. So almost correct to what we are estimating from the very simple state. We got 1.6 into 10⁴ into 10⁶, but it is also like 10⁷, because it includes more sophisticated physics in terms of all the composition, opacity. It is not the straightforward one. Density is also like this. But you see, in the surface, everything gets broken down. So that is the lecture of this, all of this. Krishna, Vaibhav, they will tell you the surface is also very notoriously difficult to do the physics, because in the high layer, there is a radiation physics is going so badly. There is no thermodynamic equilibrium. All are in NLT. So everything you need to take care. So that's why they zoomed out, because at the surface, because when you see photosphere, you know, our sun, it is not exactly defined in that way. So there will be tiny variation. So that's why you see there is a deviation, and you cannot constrain them properly. So this is your standard model, and this is X, Y, and Z. Inside, these are like the free parameters. Inside the code, you do not know what is happening. Surface, you know. So inside this, they take it as a free parameter and see whether it is producing the surface observation. In crudely, in that way, you can assume. Then this is the how this X and Y varies, like hydrogen from the center to this. So this is we get from the theoretical model. So we will show you how I'm doing in the time. We have something. So this one is your standard solar model. So now we'll come into the heliosismology, that how we are actually, then I will show you that how it matches with the standard solar model. Then we will see it is doing much better job, but needs improvement. Then Yes, nevertheless, the varying input physics, like the opacity, is equation of state. Equation of state is a dangerous thing. We always assume this like the polytropic or the ideal, but actually that is not true. So we have to lot of deviation. There is the convection and the magnetic field. So that is another thing, and also diffusion coefficient. So when radiation is going and everything is a random walk process, you can assume that the convection is going as the diffusion process. So this also, if you change, then you see the result might get changed. So these are the parameters we have to indirectly constrain them because we do not have hold to get them in a direct way. So at the back, any questions or you guys are getting bored? It's fine. Okay. So now this after you develop a successful model, how many of you heard about the Arthur Eddington limit? Chandrasekhar Eddington. So Eddington, in his book, The Internal Constitution of the Stars, when the model was building, he imposed this question. You see, you develop a model and we don't believe. So what are the things? So he was a very good scientist, physicist. So he asked this first thing: is there any way of checking this correctness of this model? Are there any means of measuring the central temperature and the finding out the chemical makeup, so chemical composition? So this is he imposes that time. It was very how do I say? In the newspaper, that very hot news comes. This said everybody was trying to answer this question: whether the model you are developing, whether are they correct, and then what appliance can pierce through the outer layers of a star and test the condition within. Even many scientists that time also thought that we can never be, before discovery of the helioseismology, we thought we can never be probe inside. So that is the question, like I am also imposing to you guys. Just think that how we'll do. But eventually, in the 400 years of our study, we have done some of the things, but many things to do yet. So then solar neutrino can indeed probe the interior of the sun, because neutrino is a weakly interacting particle. It even come to the earth. So you have to put some of the detector which actually captures them. Otherwise, it won't. Then the helioseismology. So I think I will only give you now the neutrino and helioseismology, and after second lecture, I will give you the magnetic field. And it's 10:43. Okay. So now I show you the solar neutrino problem. So this neutrino problem was also there in the solar standard model quite a few times, and that was also posed questions to the high energy physicists, because they thought the model they're building for the neutrino PP reaction, they are not correct. But the solar neutrino sun was a cosmic lab where you can verify all of your theory. So this is the experiment I'm showing from 3 detector, and these are various, like I just summarize this, but there are like 1,000, like 100 to 200 like experimental setup, Japan, USA, everywhere, to get this neutrino. So neutrino get captured in 3 detector: in water, chlorine, and don't ask me why they do, because I do not know. The high energy part I do not know. Then the gallium detector. So if you see the PP reaction, that theoretically in this chlorine detector, you would assume there is 7.7 SNU capture will be happening for neutrino. For water, that is the number is like around 6 point how much? 1.0, and this is 129. So this is the different unit, but I thought that SNU is like 10 to the minus 36. So the different, it is like the different one with the error bar, of course. These are the experiments. Just you see, it's not matching. So then main conclusion is happens. So first thing, we always look for the positive thing. So the positive thing is neutrino has been detected. So nuclear reaction is happening. But how it is happening, we do not know. Second is, experimental result is significantly below the theoretical expectation. So why is so? So you know that when the neutrino is going, they have the neutrino, we do not assume the neutrino has any mass. And neutrino flavor is not changing. So these two assumptions. So now after this experiment, 3 things comes into mind. Whether the sun, all the ambience, all the environment, what we assume, is it correct? Or the neutrino is the problem? So that time that's why solar neutrino problem is very popular in that way. So we find that solar model and everything was fine. The neutrino was getting changed its flavor from positive to electron or something. So then there is a lot of experiment. The solution came, the electron neutrinos transformed to a different flavor along their flight path to interior of the sun to the earth and through the space between sun and earth. So then it has been solved. So, but we now know that the PP reaction and this Thiono cycle, like 2%, is happening based on the neutrino method. And we know where it is happening because like very cold, like 20% of the core, where the temperature is around 10⁶, 10⁷. Actually, there things are happening. So this is kind of now well-established thing. Now, this result is from 2005, 2010. I do not remember actually. So this observatory again re-verify. And they see that this is indeed true. Now we'll come to the heliosismology. But before going that, any question in the standard solar model or anything you is? Oh yeah. Oops. So you know that when we are doing this experiment. So when you have the PP reaction, when the two proton is just binding together, then they create a neutron, and that neutron is a positive neutron and electron neutron. So when you are getting detected on the Earth, you would expect the same flavor will be there. But what is happening when it is going through the interplanetary medium, our Earth atmosphere, then it changes its flavor. So whatever was happening in the origin, what you are detecting actually gets changed. So that's why they say the flavor mixture. So that was the very well-known problem in the high energy physics that time. So then the sun gives this idea, like in this way, two things get solved. One thing is like neutrino indeed change its flavor in the process, and also the solar model which we develop, it is okay. All right. That is like, suppose this chlorium and the gallium and water detectors, suppose they're given for the electron, but suppose in that moving, that flavor is not there. So other flavor just not getting detected. So that's why when they do like the more good experiment, they take care of all of them. Then they see the missing neutron is already there. So we are now going to helios. Oh, that condition I'm not sure. Maybe for high energies. No.
Initially, it was supposed that neutrinos doesn't have mass, which means they cannot fluctuate between the different flavors. But then, because all the experiments which was done, they were detecting only electron neutrons. So then, if they were actually switching flavors, then you should do experiments that detect all the three flavors. They did that experiment and they actually discovered that you have all the three flavors, which means, but the sun doesn't emit according to the reaction of all these three flavors. Which means the neutrinos coming of switching between these flavors on the path while getting detected. So that's the experiment. So having mass is the condition that switching between.
So then we go to the heliosismology. We can finish by 11. So heliosismology, this is the figure I'm giving you from 1962. So this is the Robert Babcock Leighton. So this is the person who first time just developed a Dopplerogram that time. Then he put a slit on the solar disk and see the Doppler. You know that when the velocity is coming towards you, it just frequency enhances, and when going away from you is the negative. Is the mic fine? So then they detected at that time, and they see on the surface there is a regular pulsation. So that is the first idea that actually sun is like a big acoustic resonant cavity. So when because you know the density is changing. So just like I'm speaking and the sound wave is creating, the density gradient actually changing all the acoustic node, and it is creating the pulsation on the surface. So that is the first detection. So I wanted to give you a little bit of historical, then you know that when it started. So 62 they get this pulsation, and eventually the theory was also developed. But getting this detected all over the sun and everything, because there are all other processes going, so it was not easy. So that's why it took some time from 60s to 80s to get detected everything. So this is the first theory, first observational evidence that the chance is like pulsating. So by measuring this pulses, you can actually get the interior dye, what is happening. And then, so these oscillatory motion are due to like the superposition of the millions of modes which are happening inside and creating the pulsation. So that is the first thing. So here you see they have all the 5 minutes. This is like 120 minutes they observe, and they see they have the 5-minute pulsation. Suppose one place it is pulsating, after 10 minutes it's pulsating in another place. So it is just going all over the strip. And that was the first evidence that it is indeed happening. And we now get like so much important information inside the sun from this heliosismology. And so then I just briefly give you that how things are happening. Suppose in a church or where you're just blowing a pipe, you know, the standing wave gets stand. It's just like the plane wave is propagating, getting reflected back, and you get the nodes. So in that way, suppose the wave is propagating and reflected back, you see there's a node created. So in the sun also, suppose the density gradient is going, if you go below, there's two things happening. Temperature is increasing, that's why sound wave speed vary, and the density is also changing, and it doesn't have a single profile. So when it's, so I have one photo for this. Yes. So suppose the wavefront going below, and since now temperature is increasing, it can go down and down, but remember density is also increasing. So it goes refracted back, and again comes some other places in the surface of the sun. And then when it touches the surface, now your pressure gradient simply zero there. So it again gets reflected back. So in this way, it gets like everywhere. And you have to measure with a correct observational thing that this small pulsation. And you can also develop this theoretical model that how the pulsation is happening. And how many of you do the Deutschner problem? You know, the spherical harmonic calculation. You have a hydrogen problem you did, right? So hydrogen problem, you solve wave function and everything in a spherical symmetric form. So sun, we assume the spherical symmetry. Then we first calculate how the pulsation is happening in the spherical harmonic form. Then, as it is everywhere, we give linear perturbation theory. So suppose a system is whether it's stable or not, you give a small perturbation and you disturb the system, and you see that how much displacement is causing. So same way we do here. So you have the velocity and you give a spherical perturbation and you see how much displacement, and that tiny displacement you have to measure from the instrument. And you remember when you're developing this model, it is coming from all the density. So that gives you the information of the abundances. What are the things inside? It gives you the information of the temperature. And so all kind of information you give if you measure that. So that's why helioseismology is super important nowadays. Sound waves. Spectra, velocity, light, but when it is going from there to the surface, it's creating the pulsation. So there is two. One measure with frequency of the pulsation, another was like the Doppler shift. So there are like two things. Both of them we can do.
Sound waves have velocity fluctuation as well.
Yeah.
Sound waves have both density and velocity fluctuation. So what you see on the surface can be both density and velocity. So by detecting velocity fluctuations, you are detecting the sound waves.
18. Oh, so this is your time, and this is like this different places. So suppose you take this strip. So you see this is the fluctuation over 5 minutes. But if you see the another one, there is not like all in the same time. So this pulsation might go in up, or that pulsation might go down. So that's why it's just like pulsating over there. But the oscillation of this P modes is like more or less 5 minutes. This slit. So 1, 2, 3, 4, 5. You know, they put like this 20 kilometer, I think 100 kilometer slit, and they take like each velocity. Then they measure that. But that time it was not that. Nowadays, even you get more. You see, in a 20 kilometer, you have 410. So 2 kilometer distance. Nowadays, it's like, sorry, 80,000. Thousands of kilometers. Sorry. So it's like that. And nowadays, I think resolution much better than this. So this is this solar disk is like not like simple. So it's the 80,000 strip. So when you're seeing this small one, so then each, like, you know, this is the 20,000. So each strip is like 2,000. So then a sound wave from the sun. Yeah, but sound. So that's why when the surface it is happening, we are getting the signal, spectral signal. You're right. That since it doesn't follow in the space, so you cannot. But when the detector, we are only getting the spectral signature.
That's why we are using the
Doppler shift. No. The sound wave. Oh, let me explain it. No, you said it right. So inside and everything, sound wave is happening, but this is medium is there. But when it is coming in the surface, it doesn't propagate. But we are measuring the surface. And when the sound wave is changing the pulsation, it is changing the velocity of the photosphere. And that velocity of photosphere gives a spectral signature. So that spectral signature we are measuring. Now that's a good point. Actually, this is the way we do, and you'll do a lot of analysis of during the workshop too. That when one suggestion, like when you are getting data, try to connect them with the physical quantity. That how we are connecting them. Otherwise, it will be like computer science and scientists and physicists. There will be no difference. You get data and do it. So then, yes. So this is the displacement. So I am not very much expert in this. So I know that how they are doing in this epsilon and everything. This is the displacement. And if you take the spherical mode, I think again I am giving this example of the hydrogen because you know the different mode represent the different wave function. So in this way, the different L represent the which mode will propagate inside and which mode will not. So the larger mode, they can go, they are like confined in this shallow region. So if you measure the larger mode, then you will only see the surface. But if you can measure the lower mode, then you will see the deeper layers. So this is the helioseismology is a very good problem. And then they measure all of this stuff there. So then you will get the information out of it. So I think I note down, yes, the standard model. So now the result from the helioseismology. You see, this is the deviation in the sound velocity from the standard model and the helioseismology. You see, it gets pretty much well. But when it comes to the convection zone, it is also getting this peak because there the radiation transport goes from radiation to the convection. That's why you get this. So the DTDR, remember I told you, that gets changed there. And you can actually measure where it is happening. And this is your convection zone, and below that is the radiation zone. But you see in the surface, it is much more deviated. So the standard solar model is getting deviated. The reason is we are getting magnetic field, turbulent mixing, you know, the convection when it is happening under rotation, nothing is considered. And even in the surface, the density, scale height, and the stratification, everything gets changed. But that's why in the new, this is from 1996, like the measurement. But nowadays, is Deepika has question? Okay. So then, and if you see this, the density, it's matched quite well. So whatever you are studying from your basic understanding, that actually matches well with this. So this is, I think, yes. So this is kind of end of the first part. So, right. Yeah. So that's why, you know, that was the idea given from the standard model that there might be changing, but then helioseismology found this tachocline region is happening in there. So this concludes my first part. So my idea was to give you like some of the interior structure. Then in the second part, I will give you that how this energy and everything move to the surface and the generate of the magnetic field. So if you have any question in this, I'll be happy to take. Yes. Yeah.
Feel free to ask any
Yes,
questions.
and I will also be outside. So whatever you have questions.
During the tea break, you are expected to talk. What is this one of the different types are those known?
Oh, velocity perturbation is very dynamic, and you know the radiation which is happening, it is not like only is a time steady, because with the time the nuclear reaction is happening and the some mass are getting changed. So all dynamics is very dynamics change with the time, and that keeps on changing the perturbation.
On the surface, if you're talking about their sound waves, right? So why the sound waves are being generated? Any convecting pot of boiling pot of water, if you see, all the bubbles will generate some sound.
Yes.
They're creating some fluctuations, they generate some sound. That sound is trapped inside the sun, but their signatures on the surface is what you see. That doesn't travel through space, but then their signatures in terms of Doppler shift is what you see.
Yes. Oh yeah, that's what the helioseismology, you know, that you do. You are measuring the displacement. Now you have this all the displacement, everything, the sound generation, everything is a function of opacity, velocity. So you do inversion technique. No. Yes. Yeah. And that theory is well established because it matches 1-to-1.
It's more of the sound waves actually travel inside the sun. They travel inside the sun based on how fast they travel, depends on the temperature,
density.
So how much they reflect and refract and then come back to the surface. So by studying the surface properties, you study how deep they are going, how much the temperature gradient is.
Every,
So all these you can probe.
yeah.
So using theoretical models, of course.
Of
like
course.
Gopal.
Whatever you are making, I mean, are we somehow connected to the CME?
Yeah, that will come. So you know that this whole interior dynamic, the velocity and everything is changing. That create the magnetic field. And whenever you see CME and everything, those are all related to the active region. All the filament region, granular region, right? The active region is the most important one, which is creating the CMEs and stuff. So I'll come, but to understand this magnetic field evolution and everything, we need this velocity component and stuff. So that is the part of 2 lectures, that the solar dynamo and how the magnetic field generates and everything.
What is the Y?
Oh, this is the change in the sound velocity. Suppose you have 2 quantity, then you measure delta C. Now you normalize delta C by C. So this is just like variation. So if the variation is large, that means 2 model is not matching. It's just like simple math. Okay, so if there are not many, yes, please. Huh? Right. Yeah.
This region that for low mass star
Having
having
this thing.
some radiation, then convection, and for high mass star there will
The
be
convection and
convection. Then
so you remember the high mass star, their nuclear reaction and burning is much efficient. So that can have like higher temperatures gradient. So that even onset the convection there. So this is all the mass, core mass. So that's a massive star. If you go to O type, I think O type, there the
Yeah.
convection zone is the inside because there is a massive burning is happening. So again, these two thing you study, this will be valid. But how much is the temperature gradient and the stiffness is going, that decides
that
whether it's-
requirement of temperature.
right.
So the how does the opacity play in role to?
Oh, you see the opacity region. So there, how do I say? Suppose you have a very heavier region, so the temperature cannot be easy to uplift the material, right? If you have a very thin or light material, then it will be very easy. But another important thing is like when you do the PP reaction, CNO reaction, everything, you have the massive one, the other nuclear reaction will also be burning. So that will give you the more energy. Did you
Means
can you
when we
follow?
go from center to the surface of sun, that density decreases continuously.
Density decreases, but of course density decreases. But in the inside, when the nuclear reaction is happening, that also depend on the mass. Like the other kind of nuclear reaction might happen. That's time.
Yeah.
Not only the PP. Here is the hydrogen is the only responsible part, but even the carbon burning or something
Yeah,
might
CNO
happen.
factor.
So that will be taking over that.
Yeah. Yeah.
Study something about pulsating.
Oh, those are like the pulsating. There's like 3-minute pulsation or something. That is the magnetic signature. Yeah, this is like the surface pulsation. What you are saying probably about the pulsar.
Pulsar means the radial
Uh,
The pulsating stars are global pulsations. It's more global and more towards whole star because of gravitational pulsation.
I think so. The tidal probably.
Other than these
Acoustic.
surface, like Gopal mentioned, these are just surface
Hmm,
and
hmm.
very local pulsations.
Yes, yes. No, below interior also is better, and the after tachocracy region, the convection, magnetic field, and everything. If you take care of them, then it will again match. But that I will show you just from the very old paper that how it does. But it gets reflected based on the your, how do I say, based on your density gradient. But it since the radiation zone, I think there the density is much stronger, so it doesn't penetrate that much. And also, if it penetrates, the data which is coming to the surface is very scattered. So that's why if you go below the tachocracy region, the measurements are not very reliable. So that is ongoing research now. So I will tell you in the next slide that in the tachocracy region, we are trying to measure the plasma flow, and that we are not getting very correct. So many groups are working because they're like very dense regions. So some information on the acoustic wave which is passing, it also interacts that region. So the convection zone, I would say, safe to say that they are measuring well. But if you go down after tachocline, no. Solar model, they have a one from Max Planck. Their standard solar model. I think Christian and Dalsgaard, they got some paper, award too. So they have a very good standard solar model, and they do the evolution too. And that has been used for all the solar-like star model, dynamo model. So that is came around 2006 or 7, and that matched very well with the heliosystem. So I would have given you that, but I forgot. I want to give you the very basic thing first. So, but we have a good standard. Okay, so see you after break.
So we have a tea break now. So in about couple of minutes tea will arrive, but feel free to get comfortable. We can go out. We can have tea, and then after that, maybe around 11:30, 35, we can come back. 11:30, we can come back.
Continue. But if you take it, you see the